So in the last video, you were introduced to forces and dealt with a few basic problems. In this one, we're going to be going over a few more advanced problems, such as elevator problems and system of masses. If you don't already know how to draw and use free body diagrams, I highly recommend you freshen up on that because it's going to be really useful in these questions and in the forces chapter in general. So let's do some elevator problems first. So what is an elevator problem? Now, typically speaking, elevator problem is when you have an object sitting or standing on a scale, inside an elevator. So that's our scale. And it's usually a person that they use in examples. I don't know why, but that's what they do. And they are in an elevator. Don't ask why it's floating. It just is the scale. And you usually want to figure out what the scale reads in terms of newtons in different scenarios. So in physics, the scale actually reads the person's weight in newtons and not in kilograms. So it uses the person's mass and multiplies it by whatever forces are pulling it downwards, whatever forces there are. Usually it's just force of gravity when you're at rest, and then that is what this scale will read. So let's do a few questions. Let's find out what the scale reads. Oh, we have to give the person a mass first. So let's say they weigh 70 kilograms. And let's do a few questions here. What will the scale read when the person is at rest, or the elevator is at rest, I should say, when it is moving 5 meters per second up, when it's moving 4 meters per second down, what it reads when it's accelerating 3 meters per second up, and what it reads when it's accelerating 4 meters per second down. So you can take a moment to do these questions. You can pause the video, and then I'll just go over them. So the first thing you want to do in any sort of physics problem is a problem involving forces, more specifically, is draw the free body diagram of whatever object that you're calculating for or you're observing. So in this case, we're observing the person here. So the free body diagram, when the elevator is at rest, would look something like this. So you have the 70 kilograms. So when the elevator is at rest, there's only two forces acting upon the person. There is the downward force of gravity, so we'll label this as Fg, and then there is the normal force, so we'll label as Fn. So what will the scale read here? Well, the scale will read simply just the person's mass times the force or the acceleration of gravity. So we can use the formula F equals ma. We can go F equals 70 times 9.8 and we can get F equals 686 newtons. So that answers the first question here. At rest, it's very simple because there's only two forces acting on the object, and the force of gravity is what you use. So what happens if the elevator is moving at a constant velocity or a uniform motion, upwards or downwards? Well, if you see here in our formula, the variables that we have are mass and acceleration. There's no velocity in this formula, meaning that the velocity of the elevator isn't going to affect the final answer. So for questions B and C, when the elevator is moving upwards and downwards, it's actually going to remain the same. That's because the acceleration and the mass of the object don't change at all. It's just the velocity that it's moving. And you know that when an object is in constant velocity, there's no force acting on it. So the only acceleration that this object is going through is the acceleration of gravity downwards, which gives us the same answer as the first one for B and C. So this is when we get into acceleration of the elevator, which will start to affect the reading of the scale. So for question D, you want to draw the free body diagram again? kilograms. And you want to draw all the forces. So there's still the force of gravity. Oops. Fg. Still the normal force. Fn. But there's also another force pulling it upwards because it's acceleration, right? I should make it clear that the scale is reading the normal force of the object. So what the scale is actually reading is this force. And as you know, that the normal force is just the counteracting force of the force of gravity. So that's just something that you'll need to know. So for this question, there's the normal force and there's also another force of the elevator going upwards. So I'm just going to draw it as another line here. But typically you just want to make the normal force line a bit bigger. But this is just for clarity purposes. So how would you go about this question? So you use the same formula, F equals ma. And you know m stayed the same. But you know F is different. There's two different accelerations here. You have the acceleration of gravity and you have the acceleration of the elevator going up. And since you're using the normal force, they're both going to be positive here. You simply just get the 70, it stays the same. And you can get your two accelerations. So the first one is 9.8. And the second one is just 3. So you add 3 here. And you get 9.8 plus 3. This is equal to 12.8. So you get F equals 70 times 12.8. And you get F equals 896 newtons. So that's your answer D. For E, it's a really similar idea, except that you just get another one moving downwards. It's a big box. You get 70. It's the same idea. You have the force of gravity, G. You have the normal force, but you also have the other force of the elevator going downwards at 4 meters per second squared. That's another one right there. And the idea is essentially the same thing. You go F equals ma, F equals, and the mass stays the same, so it stays the same, 70, and then you get 9.8. But this time, since the acceleration is downwards, you're going to subtract the 4. So minus 4, and you get F equals 70 times 5.8. So 70 times 5.8. You're left with F is equal to 406 newtons. So one more idea that I want you to think about is what would happen if the cable of the elevator broke and the elevator is just falling, and then you're inside the elevator, but you're not on the ground, you're also in the air falling with the elevator. This is what you call a free fall, and you'll feel weightless because there's no normal force applying on you, and the elevator is going down the same way. So with that, we can transition over to the next problem, which is a system of masses. So what is a system of mass in the first place? So a system of mass is usually system of multiple objects. So typically so far you've been working with single objects where you can draw a free body diagram for one of them. System of mass is when there's two objects often connected by a string, rope, or a cable of some sort. So let's say we have two boxes here. And we're going to connect them with a rope per se. So with questions like these, where you have the two objects connected by a rope or a string, you're going to have something called force tension. So force tension right there, that looks really bad. And force tension right there. That's just the tension of the string, rope, or whatever. And I'm going to teach you how to calculate this. So let's say the first box has a mass of 4 kilograms right here. And the second one has a mass of 5 kilograms. And there is a force of 50 newtons. I should do that this way. 50 newtons. Pulling it to the right. So I want you to calculate the force of tension on both of the boxes. So you want to simply just draw a free body diagram first, just to help you understand what's going on for each of the boxes. So the first one is 4. It has gravity, the normal force, so Fn. Oh shoot. And it has Ft here. So it has 3 forces applied on it. The second box is the same story. 5 kilograms. It has force of gravity, the normal force, and it also has the force of tension, but it's going the other way, as you can see up in the diagram. The force tensions are in opposite directions of each other. So how do we calculate the tension force in the first place? Well, first we want to treat this system here as a single object, not two different ones. So what we first need to do is find the acceleration of this system. So we know it has a force of 50 newtons pushing it to the right. And we're going to be ignoring friction here, so don't worry about that. So if you know according to Newton's second law, we have F equals ma. You should be comfortable with this. We've just been using it the whole time. And you want to see which ones you have and what you want to solve for. We want to solve for acceleration. So we're going to move acceleration to the right. And then we're going to have the force 50 newtons over, what we're going to do is we're going to add both the masses together. So you're going to have 4 plus 9 at the bottom here, or 4 plus 5, which equals to 9. We're going to add both of them together, and that's how we're going to get the acceleration. You just flip around the formula a bit, just to get what you need. So you go 50 divided by 9, and you get an acceleration of 5.5 meters per second squared. So now we have the acceleration, so now what? Well, we have the acceleration of this whole system, which also means we have the acceleration for each individual box here, each individual block. So that means this one is going at 5.5 meters per second squared. And so does this one. They're both moving at the same rate because they're connected by the same, or they're in the same system. So in the free body diagram, we know that so to calculate the force tension, what we need to find out is, well, we can choose any one of the blocks. So let's show with the first one, the 4 kilogram one. So I'll just redraw the free body diagram here real quick. So what's the F net of this block? Well, we know that the force of gravity and the normal force are going to cancel each other out, so that equals 0, which means we're left with the force tension. So the F net of this box is the tension force. And then how do you calculate force again? Well, the formula is right here. So to find the total force of this one block, we just use that formula. You get F equals 4. And then we use this acceleration here, because that's the acceleration of each of these blocks. You get 5.5. This one looks really ugly. 5.5. So you simply multiply those together, times 4, and you get F equals 22 newtons. And that F is actually equal to the Ft. So that is Ft. But what we've done is we just calculated Ft for the 4 kilogram box. So what does that mean to help calculate the other one? So we've actually just calculated both of the force tensions, which is one of them, because the force tensions are always the same. So what if we take this a step further and we draw something? So let's say you have a block here. I'm just gonna draw like that. Let's say that weighs, say it weighs 6 kilograms. And we have another block hanging here. And let's say that weighs 3 kilograms. And they're connected, but they're connected via a pulley. So this is what a typical pulley problem is going to look like. You're going to encounter a lot of these in this chapter. So what we want to do is calculate the acceleration of the whole system and calculate the tension, the force tension on both of these boxes. And as you just figured out, that the force tension of one of them is going to be equal to the force tension of the other. So what we're going to do here is just start off with finding out what forces are acting on each box, which is where we draw our free body diagram. So let's take the 6 kilogram box. So it has the force of gravity, G, the normal force, and it has a tension force. And let's take the 3 kilogram box. It has force of gravity and force of tension up there. This has no normal force because it's not sitting on an object or sitting on the ground or something. It only has Fg and Ft. So what can we do here? We can cancel out these two because they're going to be equal to the same. And we're going to see what force is pulling this entire system forward. So what you want to do is treat this as one object, one whole object. We'll do that in a bit. First, we want to figure out what is the force pulling down on the 3 kilogram block. So you have gravity here, which is 9.8. So you simply just do 3 times 9.8. And you get 29.4. This is simply just F equals ma newtons. So that's pretty much the only force that's acting on this whole object, if we treat it as one. Because as you know, both these Ft hues are the same, and they're going in opposite directions, they're canceling each other out. So if this and this cancel each other out, both of the force tensions cancel each other out, you're only left with this over here that's moving this entire system. And that, it's 29.4, that's the force that is moving this entire system. So we want to calculate the acceleration of this system. So since we have the force here, that's the only force acting on the whole system, we want to use it on the mass of the whole system. So to calculate the acceleration, we use the same thing we did before. So A equals F over M. And you have A equals 29.4 over M, which is the whole system. So you can write M sys here for the system. And we have 6 and 3, so you get 9. You just add them together. And then once you divide them, 29.4 divided by 9, you get 3.3. A equals 3.3 meters per second squared. Yeah, 3.3 meters per second squared. And now we define Ft, since we just calculated the acceleration of the system. And to find Ft, we can just use any block because they're going to be the same. So we'll just go with the first one here. So Ft here, you have the acceleration and you have the mass. So you can just simply use this formula. F equals ma. You have F equals 6 times 3.3. Because if you look at the free body diagram, I'll just draw it down here once again. 6 Fg, Fn, Ft. You know, these two cancel each other out, and this is the only force right here that's acting on this block. And since it's the only force, you only have, you know, the acceleration, you can just calculate what that force is. So the Ft of the first block is going to be equal to 6 times 3.3. Which is equal to 19.8 newtons. And as you know, the force tension here of this block and the force tension of the other block are the same. So you have actually just calculated the force tension for both blocks. That's typically what you would want to, in these questions, it's typically what you're asked to do. Find the acceleration, find the force of tension. And yeah. For these questions, we did ignore friction. So if there was friction, how we would go about doing that is just subtracting the force that you get down here. So this force here, you just subtract the friction force from that. So yeah, that should pretty much be the bulk of the questions you'll encounter in this chapter. A lot of elevator problems, a lot of pulley problems like this. So if you're still a bit confused, I can quickly just gloss over how to go about this. You want to calculate, first you want to draw the free body diagrams. You always want to do that just to help you understand. And you're going to know that the block that's on the table per se, it's only going to have the force tension pulling it because the force of gravity and the normal force are going to cancel each other out unless, I don't know, they're on an elevator and they're going up, but you're not going to encounter those kind of problems. And you know that the force tensions always are equal to the same, so you can cancel each other out because they're going in the same direction. Because another way you can look at this problem is just similar to a problem that we did, the problem up here. You can look at it like this, because what the pulley does is just make it, the horizontal go vertical. You go 3, 6, and then you know gravity, acceleration this way is gravity, because it's going down here, and you can just simply look at it like this, and you can find the force, which was 29.4. And then that way it's just similar to this problem that we did over here. And then once you do all that, once you calculate the driving force, because you know this and this cancel each other out, that and that, so you only have one force driving it, you can use that force to calculate the acceleration of the system, and from there you can calculate the tension of one of the blocks, and then the other block will be the same. It's really important to know when you should consider the whole system as a single mass or a single object, or when you should look at them individually, because if you mess up on that, you'll mess up on the answer. So with that, that should do it for this chapter. And thank you for watching.